Slopes. Here are your priming questions. Slopes, more than meets the eye. All of you have learned what a slope is. Now you're going to be learning about what a slope means and what you can understand about the object's motion when we're talking about carts that are moving or objects that are falling or just objects in motion. The first thing that I want to mention is the different types of graphs. The first one that we're going to start with is displacement versus time. This is often what we refer to as a dt graph. Then we have velocity versus time. This will be what we call a vt graph. And then we have an acceleration versus time, which we call an at graph. And that just simply tells you what you're dealing with for your axes. Now, typically, we're going to have our time on the x-axis. This isn't going to be 100% of the time, but the vast majority of the time that we have these graphs, or any graphs, we're going to have time as our x-axis, even if it is the dependent variable. So keep that in mind. So dt graph, displacement versus time, time on the x. And as a quick reminder, slope is simply rise over run, so how high it goes and then how far over it goes, or how low and then to the side. So if we look at these graphs, you can see that they are all lines, which means that the slope is constant. In this case, when you look at this, the easy way to look at this, if we were just to draw some dots along the line, we could have these 2 points, and we can measure the displacement, the positive displacement in this case, so how much it goes up. We could also measure how far it goes to the right, meaning how long it took to go up that displacement. So from this, we can figure out how far and how long. And so this is a positive slope because it's going up and to the right. We'll talk a lot more about these slopes in just a moment. In this case, when we look over here, we can see that our slope is 0. It's a horizontal line. This is our VT graph in this particular case. And we can say that the slope value is 0. And in this particular case, we can say that the velocity is constant. Whatever the value is over here, it doesn't change. So this particular object has the same velocity over time. And if we look over here at the acceleration versus time, the AT graph, you can see that not only is the slope 0 and horizontal, but it is at the 0 mark. And so we can say that this object is not accelerating. What's interesting about it is just because it's not accelerating doesn't mean it's not moving. It could have a constant velocity. And we'll talk a lot more about that later. So, some interesting notes. The slope at a point on a dt graph tells you the instantaneous velocity at that time. If we think of the rise over the run as the displacement over time, we can think of this as the change in displacement over the change in time, delta d over delta t, and that is equal to our velocity. So in the same way, we can make this go a little bit further. The slope at a point on a VT graph tells you the instantaneous acceleration at that time. And this will be another new equation for you. So we have the acceleration is going to be equal to the change in velocity over the change in time. This is commonly written as A is equal to V over T. And remember, this V over here is the change in velocity. So acceleration is equal to the change in velocity over time. Let's take a look at a few different graphs. So again, we have this graph. We can see that it has a positive slope. It's going up and to the right, and it is a line, so it has a constant slope. So regardless of where you would draw your point, these would all have the same slope value. If this were a dt graph, what that tells you is that we have a constant velocity. It is going at the same speed and direction the entire time. Now, let's take a look at a different graph. Let me erase these points. Let's look at this graph now. We can see that this is going down and to the right. And so in this case, we would say that this is a negative slope. And if we're looking at a dt graph, we can say that this has a negative velocity. And it's constant. The second to last one is going to be the horizontal line. We've talked about this. In this case, if we have a dt graph, the position over time remains constant, and the slope is 0, which means the velocity is 0 in this case. Remember, change in displacement over time is equal to velocity. If your displacement isn't changing over time, your velocity is 0. That's your slope. And the last one I want to show you, here at least, is a changing slope. And so you can see that at the beginning, we have a steeper slope. And actually, let me use a line for that. So we have a steeper slope at the beginning. And that's not working right now. So we have a steeper slope at the beginning. Here we go. All right. Like this. And from here, we could measure the slope of this line, and that would be the slope at that point at the very beginning. And this would give you the instantaneous velocity, so that if we were to pause or freeze frame it, you would be able to measure the velocity at that moment in time. And if we were to keep drawing slopes here, like this, what you should see is that there is a trend now that as time goes forward, so as we go to the right, the slope of the dt graph becomes less and less. Now, the slope is still positive, it's still going up and to the right, but the slope value is decreasing. So the slope value is decreasing, the slope is still positive. As a quick note, what you should notice is that our tangent lines, these slope lines, they need to touch the graph at only a single point without intersecting through the graph. And this is how you'll want to make sure to draw your own slope lines when we do this in our lab. So you draw your slope lines, touch the graph at only a single point, and they are tangent. And then you can measure the slope of that line to find the slope value. And if we're working with a dt graph, that tells you the velocity. Some general key points about slopes. You need to pay attention to whether the slope is positive or negative, and independent of that, whether the slope is increasing or decreasing. So you can have a decreasing positive slope, like what I just showed you. You can have an increasing negative slope, or an increasing positive, or any combination of these. Now, depending on what combination of these two sets of characteristics are, that will tell you about the motion of the object: forward, backward, accelerating, decelerating, not moving, etc. We're going to do more practice in class, and you'll see that more. So let's do a single practice set first. So again, we've already talked about this one. We've said that this is a constant negative value, which tells you we have a negative velocity, which in this case means it could be the object is moving backwards. This next one is the one I want to spend more time on. We've already talked about this one over here, so we already know that this is a positive and decreasing slope. When you look at this parabola, what you should notice is that it's easiest to talk about it in two halves, which means let's go and split it in half first. And we're going to have a beginning half and then an ending half, and you can see that they're symmetrical, but you want to be careful with the way you describe the slope here. In this case, we start drawing our slopes, and we can see that it is a very large value in the positive slope. So we have a very steep at the beginning. What you should notice is similar to this one over here, the first half of this graph has a positive decreasing slope. So you start at a high value, and ultimately you'll get to a zero value when you hit the middle mark. From here, we can say that for the beginning of this graph, we have a decreasing positive slope. For the second half, what you should notice is that we begin to go into the negative slope, and you can see that it is increasing in value. And so we can say for the second half, the slope is negative and increasing. We'll talk a lot more about this in class. And here are your priming questions again.